свою картинку в сторону вот с этого, со слайда. Ну, куда-нибудь. Ну вот эту внизу твою, вот сдвинь куда-нибудь ее, маленькую. Картинку, нет, на экране. Она загораживает часть слайда твоего.
Сейчас?
Нет, другую, свою, где ты показан.
А я себя вообще не вижу.
А, ты вообще не видишь? Может, это она у меня на экране, твоя физиономия?
Full screen есть тут?
Он сделал, Камиль Ибрагимович, все, давайте не будем. Все сделано. Он сделал, он уже не может это делать, понимаете? Так. Он сделал.
Все?
Так. Сейчас. Так.
Сейчас еще, пока выключишь, дай-ка мне еще раз попробовать микрофон. Вот так. Сейчас. Скажи что-нибудь.
Я говорю тебе, здравствуй, Георгий.
Окей, здравствуй.
Ты слышишь, это очень приятно. Так, ну что, мы начнем тогда, наверное?
Да, сейчас один вопрос.
Да.
Вот так лучше с микрофоном или?
Убрать? Убрал.
Нет, я спрашиваю, как лучше, когда я с микрофоном или когда я без?
Когда ты с микрофоном лучше. Ну что поделать, такова жизнь, Георгий. О, красавица. Вот. О. Все, Георгий.
Может, тоже на весь экран сделать?
Или там.
Вот там. Это уже есть.
Там есть full screen.
Вот это. Так, сейчас настраиваем. Так, хорошо. Ну все, в принципе, Георгий, я думаю, можно начать. Начнем?
Все, начнем.
Давай.
Hello, everybody.
Так, стоп. А ты включил экран? Георгий, тебя не слышно. Алло. Георгий, тебя не слышно.
Меня не слышно?
Вот теперь слышно.
Okay. So, this talk is about number theories based on computability logic. I will be using the abbreviation COL for it. So, first of all, is computability logic. This is an approach introduced by myself some time ago, and I characterize it as a formal theory of computability in the same sense as the classical logic is a formal theory of truth. So what does this mean? Let us compare the two logics. This is classical logic. It's a simple semantic substitutive rule. Formal truths, statements of group of statements. And the main utility of classical is that it provides a systematic answer to questions is.
Георгий, извини, ты опять убрал свой микрофон?
Так.
Вот так хотя бы говорю. А то там плохо слышно без микрофона. Давай, продолжай, извини.
То, что я... Теперь я очень плохо слышу. Свой же голос обратно. Может быть, вы можете свой микрофон немножко там потише сделать, чтобы...
Так, сейчас попробуем. Говори.
Просто вы выключили ваш микрофон, теперь он нас вообще не слышит.
Алло, сейчас вообще не слышу. Сейчас.
Георгий, ну ты попросил, чтобы мы выключили микрофон. Я выключил микрофон.
Хорошо, я просил не выключить тебя потише сделать. Ну,
нет,
ладно,
тише
сейчас...
не получается.
Да, ну ладно, сейчас лучше. Просто один вопрос, должен я сначала начать или продолжить, потому что не очень-то приятно будет смотреть.
Ну, начни тогда сначала. Тут вот еще один, так сказать, товарищ подошел.
All right, начинаем. This talk is about number theories based on computability logic. I will be using this abbreviation for it, COL. So first of all, what is computability logic? I characterize it as a formal theory of computability in the same sense as classical logic is a formal theory of truth. Now, what does that mean? Let's compare the two logics. Here is classical logic. The central semantical concept there is truth, as we know. Truth is a property of statements, so formulas there represent statements. And the main utility is that it provides a systematic answer to the questions like, is P true, or rather, is P always true? Or does truth of P always follow from the truth of Q? Of course, one of these two questions is a special case of the other, but anyway. Now, what is computability logic? How does it differ from this? As you see, everything is the same, except that truth is replaced with computability. So, central semantic concept here is computability. We no longer talk about just truth, but rather computability. Sometimes we do have computability, sometimes we don't. Now, formulas represent no longer just statements, but computational problems, because computability is a property of computational problems. And it provides an answer, systematic answer to these questions. Is P always computable? Does computability of P always follow from computability of Q? Moreover, it also additionally provides, it provides these two answers in a constructive sense. Namely, when it establishes that P is computable, it not only merely establishes existence of computation for P, an algorithm for P, but rather also tells us exactly how to compute P. So we can always extract an algorithm. And similarly, it tells us how to construct an algorithm for P from an algorithm for Q. Things are naturally arranged in such a way that classical statements, predicates, propositions, predicates, turn out to be special cases of computational problems. Then classical truth is a special case of computability, the simplest sort of computability. And eventually, classical logic becomes a conservative fragment of computability logic. Conservative fragment in the sense that the language of computability logic is bigger, more expressive. It contains classical logic just as a fragment. But if we restrict the language back to that of classical logic, only allow formulas of classical logic, we get nothing less and nothing more than what we have in classical logic. So the same principles will be validated exactly as in classical logic. So, what are computational problems? How do we understand computational problems? If you go back to church, computational problems are just understood as functions to be computed. But for us, our understanding of computational problems is more general. Namely, for us, a computational problem is a game between a machine and its environment. So functions are just special cases of such games, very special sorts of such games. But otherwise, here we have more interactive computational problems of arbitrary degrees of interactivity. In fact, while functions are essentially the problem of computing a function is not very interactive. There are only two steps involved there: input and output, right? So these symbols, top and bottom, will be the symbolic representations of machine and its environment. Logical operators now represent operations on games. We say that a machine, and so when I say a machine, I don't specify, I don't define exactly what is meant by a machine, but let's understand it as an algorithm. So instead of a machine, you can always think of an algorithm, some interactive algorithm, some mechanical procedure that can be followed blindly mechanically, and so that the goal is achieved. So a machine, we say that a machine wins or computes or solves a game problem G if this machine wins G regardless of how the environment acts. Such a machine is said to be an algorithmic solution or algorithmic winning strategy for G. A problem is computable, or a game is computable if it has an algorithm solution. Now there is a whole zoo of logical operators, a couple of dozen of them, but in this presentation we only need these. So here, this is just a modest fragment of the language of computability logic. Here you see all operators of classical logic. And this is something in addition to that. These operators are, just like all operators, are operations on games. Now, something more general than these classical operators. This generalization happens in a conservative fashion, so they preserve classical meaning when applied to statements that are classically meaningful. But otherwise, these operators are operations on games that generalize their classical counterparts. A run of a game is a sequence of moves, each move prefixed with top or bottom to indicate which player has made the move. So I'm not giving any formal definitions in this presentation, but of course they do exist. Atomic sentences. Well, because we're going to talk about arithmetic, so let me, all my examples here are from arithmetic. Atomic sentences, such as this one, are moveless games. That is, games where the only legal run is the empty run. This is the empty run. This empty run, such a game is won by the machine if the sentence is true in the classical sense and lost if false. This same can be seen to be the case for all formulas built from atoms using this classical shaped operators, once we define those operators. So this sentence or this sentence, both of them are understood as the game automatically won by the machine, or more precisely the empty run, the only run of it, is won by the machine automatically, and these two are games automatically lost by the machine. These two problems are therefore computable, namely computable by a machine that does nothing, no moves, doesn't make any moves, while these two are incomputable. Anyway, the bottom line here to remember is that formulas of classical logic represent moveless games. So that's why it was mentioned that classical statements are special cases of games, namely they are moveless games, moveless sorts of games. Now, you can say what kind of a game is it if there are no moves in it. Well, let me remind you the situation with the concept of zero. The Romans did not have this concept, and the European tradition for a long time resisted this idea, did not want to accept zero as a legitimate number, because, well, the attitude was that, okay, a number is supposed to be represent some quantity, and 0 means no quantity at all, so what kind of a number is it? But now we know that we cannot do much in mathematics without 0. So similarly, these moveless games make perfect sense. They make perfect sense under our approach. Now, let us look at the game operations on games that we will be using. First comes choice conjunction. So the choice conjunction of these two games, A and B, written this way, and it is read A and B, and B. So and is because it's a conjunction, and ch is just because it is a choice sort of a conjunction. So this is a game where the first legal move is by the environment, which should choose between left and right. So these two moves, two available moves. And after that, the game continues according to the rules of the chosen component. And this choice is not only a privilege of the environment, but also an obligation, because if the environment fails to make a move, make a choice, then it loses, so that the machine will be considered the winner in this case. Choice disjunction, chore, so A chore B, is similar, with the difference that here it is the machine which makes the first move and which loses if no such move is made. So the roles are interchanged here of the machine and the environment. Then choice universal quantification. It is in fact a big choice conjunction, in the sense that so this game it is read as cho x a of x, choice all cho x a of x. This is a game where the first legal move is, again, just like in the case of conjunction, by the environment, which, rather than choosing between left and right, simply chooses a natural number, or rather some decimal representation or binary representation of that number. And after that, the game continues as A of n. Again, if no such move is made by the environment, then the environment loses. Choice existential quantification. Check systs x A of x is similar, with the difference that here it is the machine which makes the first move and which loses if no move is made. So here's an example. This is a run consisting of two moves. The first move by the environment, the second move by the machine. It's a run of this game that we see here. So what does the first move mean here? The environment chose 6 here. So for x, it chose 6. After which the game continues. So yeah, this was the original game, right? So after the environment chooses 6, the game continues as this one. Now it is the machine who can move. So as you see, the machine has made its move left, meaning that this component, the left component, was chosen. So now the game continues as this one. And it also ends as this one because there are no further moves that can be made. And the machine wins because here this is a true proposition. So true propositions are automatically won by the machine. Negation, read as not, it's a role switch operation. Machine's moves and wins become those of the environment and vice versa. More precisely, for a run phi, let the negative image of phi, let it mean the result of changing all labels in this run to their opposite. For instance, the negative image of this one is this. Then given a game G, not G is the game whose legal runs are the negative images of those of G, that is, moves have the environment and the machine have interchanged their moves, and where a given player wins a given run of the game if the other player wins, in the sense of G, the negative image of that run. Example, the negation, the negation of this game. So as we remember, negation interchanges roles, right? So this was originally a choice universal quantifier, where the environment had to make the first move. Now the roles are interchanged in negation, so now it is the machine that can make the first move. That's why it has become a choice existential quantifier. And similarly, not only the moves are interchanged, but also winners are interchanged. So even becomes odd, because even is won by the machine event only if odd is won by the environment, lost by even is won by the machine if and only if odd is lost by the machine. So winners are interchanged here and here, and disjunction becomes this disjunction becomes a conjunction. Well, we can see that De Morgan's laws remain valid with these choice operators, and not only choice operators, but well, computer logic has several sorts of conjunctions and disjunctions, as well as quantifiers, and with all of them, De Morgan's laws remain valid. When applied to an atomic sentence S, or any moveless game, the negation operation behaves exactly like the classical negation, because the negative image, so the only legal run in in games represented by atomic sentences, we know it is the empty run, and the negative image of the empty run is the same empty run. So only the winners are interchanged, no moves to interchange, and so the machine wins this run, empty run of S. In other words, S is true if and only if the environment wins it in game not S. That is, S is false. So exactly like the same as what we have in classical logic, and the same can be seen the case with all operators that look like operators of classical logic. So when applied to moveless games, their behavior is simply coincides with their classical, their meanings coincide with their classical meanings automatically, besides, not just somehow artificially made so, but as you see, it all happens automatically, naturally. Double negation, the double negation principle remains valid because interchanging the roles of the two players twice brings each player to its original role. The parallel conjunction of games A and B, it is read as A and B. It's a game where A and B are no made between the two. By think of it as a play on two boards, and in which, in order to win, the machine needs to win in both components, both A and B. To indicate in which component a given move is made, it should be prefixed with left dot or right dot. Parallel disjunction 4 is similar, with the only difference that here for the machine, in order to win, it's sufficient to win in just at least one of those two components. Here's an example. What we see here is a legal run. So this one is a legal run of this game. let's follow this run. So when the first move is made, this move is made. Look what is the meaning here. The environment makes this move, and in the right component, here in this component, it chooses 6 for x. So the game continues as this one. So nothing happened in the left component. The next move, the machine chooses in the left component, in this part, the machine chooses the same number x for x, the number 6 for x. So now the game continues like this game. Again, this move, the environment, by making this move, the environment chooses in the left component, it chooses the left component, left dot left. So the game continues as this game. And finally, here, the machine chooses in the right component, the machine chooses left. So the game continues as this, and it also ends as this one because this is a moveless game now, and the machine wins because it is true. Because it wins in one of the 2 components. Parallel implication is simply an abbreviation, understood as an abbreviation in the standard way. But intuitions, the computational intuitions associated with it are perhaps most interesting because intuitively it can be seen to be the problem. This A implication B, or rather implication B, P again stands for parallel, so A implication B is intuitively it's a problem of it's the problem of reducing B to A. So here's an example. Let holds x, y, that did mean Turing machine x holds on input y, this predicate, and this is about acceptance, so Turing machine x accepts input y. Then the holding problem as a decision problem is expressed this way. You see, the environment chooses x and y, there's a particular values for x and y, and the machine should reply, say whether it holds, or x holds on y, or it does not hold on y. And similarly for the acceptance problem, so this formula here, this part represents the acceptance problem as a decision problem. So this x and y are inputs, and left or right are output. Now the whole thing, this implication of these two, you see, each of these 2 problems is known to be undecidable, but the implication of from one to the other can be shown to be computable, and the winning strategy here relies on the fact that indeed one can be reduced to the other. Roughly it goes like this. Wait till the environment makes a choice here in the right component, because the machine itself, you see, the roles are interchanged in this game now. So here it is the environment that can make the roles are interchanged in antecedent. You see, under normal circumstances, it would be the environment's choice, right, x and y. But now, because the roles are interchanged, it is the machine who can make this choice as x and y. Anyway, the machine waits till the environment makes a choice in the consequent, so chooses some particular m and n. So now the machine has to tell whether m accepts n or not. What the machine can do is to choose the same m and n in the antecedent, so the game continues like this, and then again here is the machine who can make a move, here is the environment can make a move. The machine, it's wise for the machine to wait, not to hurry. So both players have moves here, but is better off just waiting for the environment to make a move, because if the environment fails to make a move, the environment will be a loser in this component, and which makes the machine to be the winner in this full combination of games. So the environment has to make a choice here to avoid losing the game, and the choice should be holds or does not hold. So if the environment says that M doesn't hold on N, then the machine chooses not accepts M, because if it does not hold, then that means it doesn't accept either. If the environment chooses hold, tells us that M holds on N, then the machine chooses no. After that, the machine needs to simulate the work of this machine M on input N, and the simulation will show whether that holding was with acceptance or rejection, and correspondingly it can choose one of these two components. Finally, blind quantifiers, exists. This existential quantifier is defined, can be defined as the dual of universal quantifier, as always as with the other sorts of quantifiers for that matter. So let's only look at this blind universal quantification. So in this game, no value for x is specified. The machine should, in order to win, the machine should play blindly in a way that guarantees success in A of x for every possible value of x. So it doesn't know what x, whatever it is, it should win. And if so, then the machine is the winner in this game. So no move, unlike the choice quantifiers, no move is associated with this or this. Let's look at an example. This game. So, what's the meaning here? In this part, it is the machine. The environment chooses a number y, and at which the machine has to tell whether x plus y is even or odd. But it doesn't know x. Can it still tell whether x plus y is even or odd? Yes, it can, if the machine is told whether x is even or odd. We don't need to know exactly what x is, but at least if we know whether it is even or odd, then we can indeed solve this part of the game. So the game, according to this run, the environment in the right component, the environment chose 5. So this way the machine has to tell whether x plus 5 is even or odd. The machine continues waiting, because here here it is the environment who needs to make the move. It's the antecedent, right, in this junction. So if the environment made the move, this move, so it chose odd x here. So now the game continues this like this, and now you may guess the machine should make what choice? Which of these two components? This one, because 5 itself is odd, and if x is also odd, then odd plus odd is even, we know. So notice that this quantifier never disappeared, it remained as it was, and so did the implication operation. Generally, the classical structure of a game, when it evolves in this fashion, will remain unchanged, and it will be only these choice parts that really change. In this game, obviously, it is the machine who wins. In this run is won by the machine, because, the run hits a true proposition. Alright, so that was a survey of the operators. And now, interactive complexity. You see, in computability, the standard concepts of time and space complexities are naturally and conservatively generalized to the interactive level. So can be applied, become meaningful, this concept become meaningful for games. Also a new complexity measure is introduced called amplitude complexity. It is concerned with the sizes of machines' moves relative to the sizes of environments' moves. And instead of computability in principle, we can just as well, just as meaningfully speak about computability with limited resources, amplitude, space-time, like polynomial, for instance, polynomial space computability rather than just computability. Right? These problems here all are polynomial time computable. So, and what does that mean in standard terms? So the first one expresses the decidability of the identity predicate, right? And now, because we're talking about polynomial time computability, that simply means polynomial time decidability of this and this. So this is the problem of deciding the identity predicate in polynomial time, and it is solvable in polynomial time. The meaning of the second one is that this operation of addition plus this function is computable. Polynomial time computable again, because we are talking about polynomial time computability. Now this one, what it says is that square root, when it exists, this one just says that if the square root exists, the square root of x, of course, we're talking exists, then such a square root can be actually produced. So square root, when it exists, is polynomial time computable. So this square root can be produced within polynomial time. And the last one can be seen as, I will not try to explain exactly how, but it can be seen to be the problem of polynomial time reducing P to Q. So this is computable, polynomial time computable, means that P is polynomial time reducible to Q. And polynomial time reducibility is the main concept used in the complexity theory and all those concepts like NP completeness and so on. But they are defined in terms of polynomial time reducibilities. Arithmetics, number theories based on computability logic are called arithmetics, CL or computability logic arithmetics. And they're based on computability logic in the same sense as piano arithmetic, standard classical arithmetic, is axiomatic number theory. It's based on classical logic. Usually arithmetics are in the language whose logical vocabulary is the one that we surveyed by now. And the non-logical vocabulary is standard, that is 0. It's the successor, symbol for the successor function, this prime here, plus, times, and identity. We need some preliminaries, technical preliminaries here before we proceed. So, a bound, by a bound we mean a term or pseudo-term, and we call it simply term. The term was coined by George Bullis, not by me. What's a pseudo-term? I think we know, and if we don't, it's not a big deal, because pseudo-terms are something that are not really terms, strictly speaking, but one can pretend that we do have special terms for them in the language. Nothing will change because there are formulas that can faithfully express this, carry the same meaning across the several terms. So it is safe to pretend that terms are simply terms in the language. So anyway, it is a term, a bounded term for some monotone function. And terminologically, we shall identify such a term with the function it represents. A bound class is a set of bounds clause under variable renaming. A tricomplexity is a triple R consisting of these three components: R amplitude, R space, R time. It's a triple of bound classes satisfying a certain regularity condition, which I will not show you here, but they are natural and naturally emerging. In all natural emerging tricomplexities are satisfied these regularity conditions as long as R, the amplitude component, is at least linear, that is contains all linear functions. As the space component is at least logarithmic, and the time component is at least polynomial. An R tricomplexity solution of a given problem is a solution, as a logarithmic winning strategy for G, whose amplitude complexity is upper bounded by some bound from this R amplitude. Space complexity is upper bounded by some bound from this R space, and the time complexity there is upper bounded by some bound from this R time. So, in other words, an R tricomplexity solution is a solution as an algorithm, interactive algorithm that runs in time from this class, in space from this class, and in amplitude from this class. And before we formulate our system of arithmetic, some notational conventions are necessary. Namely, this is a standard notation, by the way. So x between those two vertical bars is the standard arithmetization of function, the length of the binary representation of x, or it's the same as to say this function. So and it is an integer approximation of the logarithm of x. So we can see this whole thing as saying logarithm of x, binary logarithm of x. Then bit xy is the it arithmetizes the predicate, the least significant bit of the binary representation of x is 1. And again, it can be written this way. That's exactly the meaning. Also, when S1 through Sn are variables, we use this S underline, or it can be the logarithm of x underline. That means some tuple S1 through Sn of variables, or if it is this, then the meaning is that rather than directly those variables, we are talking about their these terms, logarithms of those variables. Now, let B be a bound class. We say that a formula f is B bounded if every Chol formula, subformula of f, has this form. See, for Chol x, such that the size of x does not exceed b. If the size of x does not exceed b, then f. And every Chikzist subformula has this form. So the ordinary concepts of bounded expressions. So B bounded means that those bounds are taken from the class B. And notice that this applies only to choice quantifiers. Those blind quantifiers are not affected by this at all. So in this presentation we'll only look at one system. There's a number of systems of arithmetic were developed for various purposes, corresponding to various complexity classes. Here we're going to look at one called CLA11, and it is a scheme of arithmetical theories rather than particular theory CLA11R for each tricomplexity R. So we have this infinite class of theories in fact. So let us pick some tricomplexity R, and now we are ready to define CLA11R. The logical basis of this system is computability, again in the same sense as logical base of piano arithmetic is classical logic, and I will not talk about it here. Let's only look at the non-logical axioms and rules of this system. So the non-logical axioms are these 10 axioms. The first 7 are exactly the so-called piano axioms. These axioms of piano, standard piano arithmetic. Well, number 7 is a scheme of axioms. Of course, this generates infinitely many particular axioms. In addition, we have 3 extra piano axioms. So in these axioms, it is required, in this particular, in this induction axiom, it's required that F not to contain this non-classical connectives. In addition to those piano axioms, we have these 3 extra piano axioms. The first one, what does it express? It expresses the computability of the successor function. So x prime means the successor of x. The second one expresses the computability of the logarithm function what I call logarithm, so the size of x. And this one says that the predicate, well, the question of telling whether the white bit of x is the least significant bit of x is 1 or not. If it's not 1, it should be 0. Yeah. So this question is decidable. Also, along with this one, CLA11R, sometimes we consider CLA11R plus TA. TA stands for true arithmetic. So it is the same, simply to those piano axioms, we should add all formulas of classical arithmetic that are true. Of course, this system is no longer recursively axiomatizable, but anyway. So, on top of those axioms, we have 2 rules of inference, 2 non-logical rules of inference, induction and comprehension. Here's the induction rule. Perhaps I should remove this bound for a while for a better perception of it. So it's a standard induction as we see, simply instead of this classical quantifier here we have the choice universal quantifier. So if we know how to compute f of 0, if we also know how to reduce f of x prime to f of x, then we know how to compute f of x. That's the meaning here. But the restriction here is that f of x should be an R-space bounded formula. So this formula, R-space bounded f, and this bound v of s should be a bound taken from R time. So not just for any x, but those x's that do not exceed this bound. We can, for any x that does not exceed this bound, we can solve the problem f of x. And then comes comprehension, and let me again read the meaning of it for it first. So let's, for simplicity, remove this bound here for a while. The meaning here is that if you can decide the predicate P, then you can generate, check this, a number such that in that number, each bit of this number, like the nth least significant bit of this number is a 1 if and only if P is true of that n. So this P, the predicate P, generates its own number in this sense. It tells simply bit by bit what those bits of the binary representation of X would be. So if P is a decidable predicate, it generates a corresponding number. That's the meaning, similar to the meaning in set theory. Again, we have restrictions here. So this B of S should be bound from R amplitude. So the induction scheme, the induction axiom in it, those two components of the tricomplexity are relevant, time and space, and in comprehension rule, it's just the amplitude component that's relevant. So, yeah, this is where the bound is used. And now we're ready to state the main result here, main theorem, but a couple of additional terminological conventions. So by an arithmetical problem, we shall mean a problem again that is expressed by some formula of the language of CLA 11. We say that an arithmetical problem is representable in CLA 11R if it is expressed by some theorem of CLA 11R. Yeah? So there is something provable in CLA 11R that represents, that expresses this problem. The thing is that the same arithmetical problem can be expressed by many different formulas. So if there's at least one of those formulas is provable, then we say that the problem is representable. And this is the main theorem now. For any tricomplexity R, we have the following, the soundness part. So for every theorem F of CLA 11 R plus what is this? Hello? Can you guys? Hello? Can you turn on your microphone, because I don't know if you can.
Так, слышим тебя нормально.
Okay. Cancel. All right. So something strange is happening. All right. So any theorem of this theory, for any theorem F of this theorem, the problem expressed by that theorem has an R tricomplexity solution. And such a solution can be automatically extracted from a proof of that theorem. Extensional completeness. Every arithmetical problem with an R tricomplexity solution is representable in CLA 11R. And finally, intentional completeness. Every formula expressing a problem with an R tricomplexity solution is provable in CLA 11R plus TA. Probably you can see right away that intentional completeness is something stronger than extensional completeness. This R parameter of CLA 11R can be tuned in a mechanical brute force or canonical way to obtain a sound and complete theory with respect to the target computational complexity. So R is a computational complexity that we can choose for this theory, and we generate a theory for that is sound complete with respect to this chosen tricomplexity. For instance, for linear amplitude, logarithmic space, and polynomial time, this combination, we can choose R such that amplitude is set of those terms, set of terms built from X using 0 successor plus. You can see that these are exactly the terms that describe all linear functions. The time complexity component all terms pulled from x using 0 successor plus and times. And again, you can see that these are exactly the polynomial, those terms that express polynomial polynomial functions. And finally, for R space, all terms pulled from the logarithm of x using 0 successor plus. So again, this can be seen as all as a set of terms that expresses all logarithmic functions. In a similar fashion, with very little effort, you can generate instances of CLA 11 for a huge variety of tricomplexities, such as these ones here, up to primitive recursive time, just name it. Potential applications of arithmetic. So there are two main motivational factors here. First of all, that this CLA 11 can be seen as a declarative programming language in an extreme sense, and CLA 11 can potentially be used, perhaps, hopefully, as a tool for separating computational classes. Let's say you want a program which computes the integer square root of this square root function such that the program runs in polynomial time, logarithmic space, and linear amplitude. All you need to get such a program, in order to get such a program is this. Instantiate the R parameter with the corresponding tricomplexity. We already saw on the previous slide such a tricomplexity. Then express your goal in the language of the system. Then the goal, if you remember from one of the previous earlier examples, it can be expressed this way. It says that for every x, if it has an integer square root, then such a square root can be found. It can be actually produced. And finally, look for a proof of this formula in the system. And once you find a proof, the compiler can extract a program from this to Summer's theorem, and that such a proof automatically also serves, that's the beauty of it, it automatically also serves as a verification of the fact that the program makes its specification. This is the specification of the program, and the proof of it is in fact a formal verification that the program meets its specification. Generally, this is a notorious problem, undecidable problem. This is program verification problem, but here it is automatically neutralized. Other than that, the proof lines can be seen as best possible comments for the corresponding steps of the program. So it's also a program commented in an extreme sense. Furthermore, well, this is from the realm of fiction at this point, but still, if we develop reasonably efficient theorem provers, step 3 is that finding a proof can be delegated to the compiler, and the programmer's job will be just to specify the target, just to write the formula like this, and that's it. So all of us are programmers because we all can very easily understand this language, and that's all you need to do. This part now, as a tool for separating computational complexity classes. In order to separate two complexity classes R1 and R2, like polynomial time and polynomial space, for instance, and some whatever amplitude, it is sufficient. Separate means that, well, show that they are not equal. It is sufficient to separate the two theories, this one and this one, you see? And separating theories should be easier than separating complexities directly. After all, we have seen some very impressive success stories when it comes to separating theories, well, the different versions of set theory, independence results and everything. And we don't have this kinds of stories for separating complexities. So far it has been just a fruitless struggle. So there is some hope here. Of course it is very it's too ambitious to say that, well, there's hope that this can be used for that purposes, because this is a notoriously hard problem, but still it is worth trying. So worth trying to solve some problems of complexity theory, separation problems, using CLA by separating the corresponding two theories. Now, the remaining 4 slides discuss related approaches, namely that of weak arithmetic that has similar aspirations, and we discussed the significant, to my mind, advantages of our approach over that. But I guess my time is up here. It's almost an hour I've been speaking, so I can stop here unless asked to continue. And if I stop here, everybody can look up this remaining 4 slides here, containing a discussion of advantages of our approach over the standard well-known approaches to similar problems. So that's it, a survey of the subject of computability logic. Very extensive survey can be found online at this URL. So I'm done.
Так, все, Георгий, да?
Да.
Да, спасибо тебе большое. Спасибо большое. Так, ну и вот сейчас, конечно, очень много нового материала, который не так уж легко на слух воспринимать сразу. Сам понимаешь, результаты, которые ты сейчас вот доложил, были получены не за 1, не за 2 дня, а за долгое время работы. Поэтому, может быть, вопросы со стороны аудитории будут к тебе сейчас. Пожалуйста, хочет кто-то спросить? Вопросы есть? Нет. Камиль Ибрагимович, нет?
Да, текст надо посмотреть.
Вот. Но тут вот такое мнение высказывают, что, конечно, много интересного доложено с твоей стороны, но для того, чтобы оценить и возникли вопросы, нужно посмотреть текст, который мы, надеюсь, издадим по результатам вот нашего онлайн-семинара. Ну, мы с тобой свяжемся, как это будет все делаться, это обговорим, вот, и ты все-таки работаешь над computability logic уже, я знаю, почти что 20 лет, да, скоро будет? Ну, с начала нулевых.
Не 20, а 15.
Ну, с начала нулевых, я говорю, ты начал уже работать, поэтому вот на указанном ресурсе, что ты вверху показал, там я опять вчера заглядывал, там есть много ссылок, и там текст для ознакомления, введения в computability logic. Вот, и надеюсь, после, ну, в смысле, это не первое, вернее, это уже второй случай, когда ты рассказываешь, делаешь доклад в Институте философии на тему computability logic. Год назад был осенью, приезжал ты в Москву, и вот сегодня онлайн-семинар. Ну, надеюсь, работа в этом направлении продолжится, Георгий, чтобы мы на этом не останавливались. Надеюсь, чтобы мы с тобой на этом не останавливались, продолжали и дальше.
Я полностью согласен с тем, что воспринять это, послушав так 1 раз, очень трудно. По крайней мере, я сам не смог полностью воспринять это. Но, значит, если у кого-то есть интерес, кому-то интересно, нужно, конечно, да, читать, почитать там кое-что.
Да, ну мы вот когда публикуем, мы там укажем обязательно ссылки вот на твой ресурс, где подробно ну, с самого начала, подробно, как и введение в computability logic, результаты, которые нам позволяют получать. Мы обязательно это сделаем, да, потому что ну, я знаю, вот, что сейчас одновременно с нами еще несколько человек слушают, смотрят вот эту видеотрансляцию, и наверняка у них возникли вопросы, на которые они хотели бы получить ответ, и после публикации всего, они, надеюсь, получат, и, может быть, уже напрямую с тобой свяжутся. Ну, дай Бог, чтобы так случилось. Я думаю, в этом заинтересован и ты, и мы, в конце концов. Да, Георгий? Вот. Ну, хорошо, тогда еще один раз спасибо тебе большое за это выступление, и надеюсь, очень надеюсь, что наше плодотворное сотрудничество в этом направлении продолжится. Хорошо, Георгий? Ты улыбаешься?
Спасибо вам тоже за терпение, за ваше время.
Не, наоборот, спасибо. У нас сейчас день, а у тебя утро, я знаю, поэтому это ты проснулся. А ты откуда, кстати, делаешь вот трансляцию? Из дома или из университета?
Из дома.
Из дома, да? У тебя такая доска на стене висит, ты сам...
Да, специально выбрал это место, если что-то надо писать.
Понятно. Ну хорошо, Георгий, спасибо тебе еще раз. Тогда до свидания. Я с тобой свяжусь, и мы с тобой там все это обговорим. Ну, как всегда, по-моему. Все, спасибо, до свидания тебе, до свидания. Так, ну все, господа. Ну, понятно, материал тяжелый, это естественно.
И потом символы не очень удобные, вот эти новые, его.
Ну,
вот эти они очень угловатые такие и не очень даже читабельные.
Нет, он просто для трансляции, для презентации, он выбрал там цвета синенькие, красненькие, так лучше было бы черненькое. Мне кажется, было бы лучше, было бы как более контрастно. Да. Это понятно. Ну, у него там действительно вот есть вот, ну, там, Villanova Джапаридзе /CL, как логик. У него там и введение, там, то есть сам текст излагается вообще в computability logic, и множество ссылок, где он, ну, опубликованных его работ, где с этим совсем нужно ознакомиться. Потому что computability logic, есть computational logic, это одно дело, а computability, это, собственно говоря, создал сам Джапаридзе. Вот этот и термин, и это направление исследований, вот он сюда приезжал, докладывал, там, в Штатах, в Нью-Йорке, докладывал, для Артемова и прочей компании, для нашей.
Какое практическое применение это имеет или чисто теоретические изыскания?
Ну как, ну это нужно, ну, для того, чтобы появилось практическое применение, нужно теорию в начале развития, понятно. В принципе, он в конце, он ведь и говорит о, на слайде, потенциальные предложения по арифметике. Он перечисляет, в принципе. Да, ну хотя он теоретик. Да, ну как, ну, должны быть теорики, теоретики, должны быть люди, которые промежуточные положения занимают. Поэтому это вполне естественно. Вот. Так что, ну, надеюсь, а так мы сделаем. В журнале у нас появится, у меня вот здесь, я заметил, я смотрел бумажки, это я распечатал себе все эти слайды, он мне уже прислал PowerPoint. Ну, мы сделаем вот эту транскрибацию, как говорится, и напечатаем обязательно его статью. Все? Одна, наверное, да, спасибо. Так. Так, сейчас нам в секторе соберемся. Так. Шатал. Wait. Слушай, а как вот это выключать?
А это наш компьютер?
Нет, это местный.
Они тоже уже?
А у них всегда вот удобно было. У них всегда было удобно. Так, видишь, здесь. Все, слава тебе, Господи. Так.
съем сейчас